To work safely, you must understand the risks and hazards you might face. Handling poisonous materials can be one such hazard. Know and recognize poison materials so you can understand how to respond when they are present. The words toxic and poisonous are often used interchangeably. Poisons describe a class of chemicals that can adversely affect your health and cause toxic results. In fact, the Occupational Safety and Health Administration, or OSHA, and the U.S. Department of Transportation, or DOT, define poisons as substances that can cause injury by chemical action when they contact a susceptible organ or tissue. The extent of potential injury depends on the specific hazards of the chemical and how much of the substance enters your system. DOT classifies poisons into 3 packing groups: Group 1, which poses great danger, Group 2, which poses medium danger, and Group 3, which poses the least danger. For example, sodium cyanide, used to extract precious metals during mining activities, is a packing Group 1 material, and phenol, also known as carbolic acid, commonly used in the production of plastics, ranges from a packing Group 2 to 3 material. In addition to assigning packing groups, a poison may also be assigned a hazard zone based on the inhalation of vapors. The hazard zone includes zones A, B, C, and D, with Zone A posing the greatest danger and Zone D posing the least danger. Zone A inhalation hazards are also known as immediate danger to life or health, or IDLH. Examples of inhalation hazard materials include phosphine, used in the semiconductor industry and as a fumigant in farming, is a hazard zone A material, and hydrocyanic acid, also used as a fumigant, is a hazard zone B material. A number of factors determine the hazard of a chemical and the potential harm it may cause. Returning to our definition of a poison, the extent of potential injury depends on the specific hazards of the chemical and how much of the substance enters your system. It's about toxicity and exposure. The health hazard equation explains simply the potential for harm. For a health hazard to exist, both halves of the equation, toxicity and exposure, must be present. Let's first examine the exposure half of the equation. If you're overexposed, toxic chemicals can adversely affect your health in many different ways. When responding to a hazardous incident, responders might be at risk for an acute health effect. This describes the adverse effects resulting from a single dose or acute exposure to a material. As with any exposure, signs and symptoms may not be immediate, but delayed by hours or even days. Chronic health effects are the adverse effects resulting from repeated or chronic exposures over a relatively long period of time, such as in the case of a worker handling these materials on a regular basis. The symptoms will tend to develop slowly over a long period of time, or they will recur frequently. By wearing the appropriate personal protective equipment, or PPE, you will greatly reduce the likelihood of exposure to poisons. Still considering exposure, another way to classify health hazards is how a chemical attacks the body. A local effect is when tissue damage is confined to point of contact. If the chemical enters the bloodstream and attacks organs and internal areas of the body, then it is a systemic effect. Organs that may be affected by systemic exposure include the liver, kidneys, heart, lungs, and central nervous system. Poisons can enter the body in one of 4 ways: inhalation, ingestion, absorption, or injection. One common route of entry is inhalation, breathing of chemicals into the body through the lungs. Solid poisons frequently generate dust which can be inhaled, and liquid poisons often will generate vapors which can also be inhaled. In the lungs, a chemical may interfere with breathing, damage lung tissue, or reduce the blood's ability to carry oxygen. Additionally, an inhaled chemical may affect other organs. Ingesting or swallowing poisons can occur in many different ways. Therefore, it is important to remember to always wash your hands after handling poisons. Smoking, eating, and drinking are prohibited in areas of a release or spill, or work areas with poisons. Exposure by absorption can occur in several different ways, through contact with skin, eyes, or mucous membranes. Poisons in any physical state, whether gaseous, liquid, or solid, can be absorbed through the skin. Absorption can take place without any visible signs of skin damage, or without any sensation of pain. The skin does not necessarily have to be broken or cut for absorption to take place. However, cuts or abrasions will greatly enhance the possibility that poison directly enters the bloodstream. Injection is the fourth route by which a poison can enter the body. Injection means the direct entry of poisons into the bloodstream. It can occur if a worker receives a cut from a sharp object that has been contaminated with poison. Another example of injection could be an incident involving a container of pressurized poisonous gas. If you stand too close to the point of release, the product can be injected into your body in a manner very similar to the way flu shots and other drugs are injected with pneumatic guns.
So far, we've discussed chemical exposure, one half of the health hazard equation. Let's turn to toxicity. What factors influence the effects of toxicity? Specifically, toxicity depends upon the chemical's ability to enter the cells of the body, the way it reacts chemically with the cell structure, and the quantity or concentration of the toxic material in the body. Toxicity is measured as the ability of a material to injure living tissue. The degree of toxicity is expressed in lethal dose, or LD, and in lethal concentration, or LC. The lethal dose, or LD, is expressed in terms of weight and refers to poisons in solid or liquid form which pose an ingestion or absorption hazard. An LD50 indicates the amount of a solid or liquid poison that is lethal to 50% of the test animals exposed over a specified period of time. Two measurements are used in generating the LD50 number: the amount of poison that has entered the body, and the actual body weight itself. There is a relationship between the weight of the person who has been exposed and the actual amount of poison that his or her body can process over time. Now let's turn to lethal concentration, or LC. The LC measures the toxicity of inhaled poisons. The poisonous material can be dust generated from a solid or vapor from a liquid or gas. The LC50 is expressed in terms of volume and refers to the airborne concentration of a poisonous material that is lethal to 50% of the test animals exposed over a specified period of time. OSHA defines highly toxic as a chemical with an LD50 of 50 milligrams or less per kilogram of body weight when ingested by rats, or a chemical with an LD50 of 200 milligrams or less per kilogram of body weight during continuous contact for 24 hours or less with bare skin of rabbits, or a chemical with an LC50 in air of 200 parts per million by volume or less of gas or vapor, or 2 milligrams per liter or less of mist, fume, or dust during continuous inhalation for 1 hour or less by rats. Now that we know something about measuring toxicity, how do we use this data at the scene of an incident to limit our exposure? Several measures provide some guidance to workers: the threshold limit value, or TLV, and the permissible exposure limit, or PEL. For practical purposes, PEL and TLV can be considered equivalent. You're likely to see either one on a safety data sheet, or SDS. For simplicity, we'll use the TLV measure in our discussion. The TLV is the recommended exposure limit for a material at or below which workers should have no health problems. TLVs are expressed in three ways: as time-weighted average, or TWA; as a short-term exposure limit, or STEL, the maximum 15-minute exposure allowed for a material with a total of no more than 60 minutes allowed per day; and as a ceiling value, or TLVC, the exposure not to be exceeded under any conditions. We've defined poisons and considered the health hazard, the exposure, and toxicity. Now, how does this knowledge help you identify the potential risk so you can better manage hazards? Labeling helps us identify a poisonous material in transport or storage. There are several requirements for placarding, labeling, and packaging which will be helpful in identifying a poisonous material. Poisonous materials are packaged and shipped in a variety of containers, such as metal drums, cylinders, and plastic bottles inside a fiberboard box, as well as bulk containers such as cargo tanks and rail tank cars. What about vehicle transport? DOT has a total of 9 classes for hazardous material warning labels and placards. These labels and placards use a variety of symbols, colors, and text to communicate the type of hazardous material in transport. For example, the placard for poisonous materials, Class 6, will have the word poison with the skull and crossbones symbol. But for poisons with an inhalation hazard, also Class 6, the placard will have the words inhalation hazard with the skull and crossbones symbol. Poisonous materials can be found in a variety of locations and environments, such as farms, where pesticides may be used, laboratories and research facilities, including colleges and universities, electronics industries, manufacturing, warehouses and distribution centers, and in illegal or clandestine drug laboratories. After identifying that a poison is involved in an incident, determine its potential health hazards. DOT requires that a 24-hour contact number be printed on the shipping papers as a source of product information. Also, you can call Chemtrec at 1-800-424-9300, which will put you in contact with the shipper or manufacturer. For many products, Chemtrec can fax you a copy of the SDS. The SDS may provide information on the symptoms that a victim may experience if exposed to the material. In assessing the potential hazards at the scene of a poisonous materials incident, also consider the physical state of the product, gas, liquid, or solid, quantity released, weather conditions like wind and precipitation, incident location, potential dispersion patterns, and effects due to local topography and proximity to water sources. The PPE needed to handle a poisonous materials incident depends upon the chemical involved in the spill, its toxicity, the amount of material released, and the route of entry of the chemical into the body. Information on the type of PPE suitable for the chemical may be found on the SDS. Anytime there is an incident involving chemicals, especially poisons, it is important to immediately isolate the area and deny entry. Once the incident commander has established control and has isolated the area, safety zones can be designated for the safe operation of responders. Remember, only a minimum number of responders wearing proper PPE and those who are directly involved in the emergency operations should be allowed in this isolation area. If personnel are injured or exposed at the scene of a poisonous materials incident, there are 2 important aspects of emergency response that must be initiated: emergency medical treatment and decontamination procedures.
Let's recap. Poisons are classified as packing group 1, 2, or 3 by DOT. Your health hazard can be assessed by calculating exposure plus toxicity. We've seen that there are 4 different routes of exposure. We can estimate toxicity based on either the lethal dose, LD, or lethal concentration, LC. Finally, we address the importance of early identification and the use of proper PPE where any risk or hazard exists. Our job often involves poisonous materials. To perform effectively and safely, we must be aware of the hazards associated with our work. Know what's ahead so you can respond the right way and contain any risks in your path.